Hi, welcome to the National Museum of the United States Air Force. I'm Dr. Doug Lantry from the museum's Research Division, and we're standing here beneath the massive and legendary XB-70 Valkyrie. The purpose of the XB-70 program was to enhance nuclear deterrence. It was meant to be a high-speed, high-altitude nuclear bomb delivering aircraft. And that was its role in the early part of the Cold War. It was an early part of the so-called triad: bombers, submarines, land-based ballistic missiles. Let's talk about the canards on the XB-70. They're a really unique design feature, and this airplane has unique geometry. The canards contribute to that geometry by solving a really important problem. They're a trim device that solves stability problems between the low speed of about 150 knots and the high speed of about Mach 3 and every speed in between. You'll see that the back half of the canard is a flap. Having a canard on the forepart of the airplane solves the problem of putting flaps on an extreme delta wing design. So what about the windshield on this airplane? Well, it's got unique features as well. For supersonic flight, a completely flat profile is necessary. So the outer windscreen on the XB-70 is a kind of ramp that transitions up and down. At slow speeds, it can transition down into the nose to give the pilots a forward view. But at high speed, that outer windscreen comes back up and covers the inner windscreen. So the crew compartment is completely isolated from that, and the outer windscreen is only for aerodynamic purposes. Let's talk about wheels. This is the front gear of the XB-70. These tires are made by B.F. Goodrich, and you'll notice that they're silver. Not many tires are silver. B.F. Goodrich developed a special heat-resisting compound that's infused throughout the body of the tire and also painted on its surface to make these tires withstand temperatures up to 360 degrees Fahrenheit. It's made possible by that silver painted compound on them, which is also infused throughout the body of the tire. The tires, in turn, are cooled up in the wheel well by a mixture of ethylene glycol circulating through brazed tubes inside the wheel well. So they're cooled by the surface of the tire, and they're cooled inside the aircraft. So here's the rear bogies of the XB-70, where the main tires are. The tires are the same as on the front, but check out this little tire here. This little one is about anti-skidding. That tire doesn't have any temperature protection because it doesn't need it. What it does is it tells the computers inside the airplane when to apply the brakes and how much. The brakes, by the way, on this airplane withstand up to about 2,000 degrees Fahrenheit temperatures. These bogies pivot like this, like the back one goes down and the front one comes up. And it just didn't pivot. It instead of like this, it stayed like that. And it just pow, and it just destroyed the back half of one of these things. There was an incident once landing one of these airplanes where these bogies didn't work like they were supposed to. The whole thing pivots front to back so that the back tires hit first and then the front tires. Well, one time, one of the bogies didn't pivot right, and so the back half of one of the bogies was severely damaged. Didn't lose the aircraft, though. Compression lift is a key feature of XB-70 aerodynamics. The area of the shockwave formation on this airplane, which is just at the front of the intake splitter duct on the underside of the fuselage and wings, creates a shockwave that increases lift in this airplane by as much as 30%. It also creates a reduced drag condition and enables the airplane to cruise quickly at Mach numbers at a lower angle of attack. Saves fuel, increases speed, decreases drag. So compression lift is a key component of the aerodynamics of this airplane. Another key part of XB-70 aerodynamics is variable geometry wingtips, these things over here. At low speeds, landing, taking off, and so on, the wings are perfectly flat, no anhedral, no dihedral. But at low altitude, low supersonic speeds, those wingtips can fold down at 25 degrees. That increases the stability of the airplane, makes it easier to control. At high speed, high altitude, those wingtips fold down to 65 degrees. Not only does that solve stability problems, but miraculously, it also increases lift. So the variable geometry of this airplane both increases lift, provides stability, and allows an airplane like this to operate in a wide range of speeds between 150 knots and about Mach 3. It's really an amazing design feature. Another thing about the fold-down wingtips is that at high supersonic speeds, because they provide extra stability, they allow the relative size of the twin upper fins, the vertical fins, to be that much smaller, thereby reducing drag. This is all very clever design solutions to high-speed supersonic flight in the 1960s. Riding your own shockwave is a feature of this airplane. That compression lift holds the airplane up, of course, or provides like 30% greater lift than it otherwise would if the shockwave didn't exist. And also the fold-down wingtips increase that lift in addition to providing stability. They allow the vertical fins on the top of the airplane to be that much smaller proportionally, which in turn reduces drag. So it's all part of a very clever design solution that all works together through some variable geometry to make this airplane a unique aerodynamic specimen. One of the most amazing features of the XB70 that you can see here in the museum is the business end of the raw power of this jet. At the back of the aircraft, you can stand here and marvel at the six side-by-side General Electric YJ93 afterburning turbojets. Now, the aircraft could achieve Mach 3 even if one of the engines wasn't working, with only about a 7% loss in range. But the bottom line for these engines is that they operate best at very high speeds. They operate in continuous afterburner, and so they're most efficient at super high speeds. And joining 6 of them together in a row like this is nothing but high-speed power. Each one of these engines develops a maximum of about 30,000 pounds thrust. Each of those engines actually was developed as, a single engine for another single-engine fighter project, which was canceled. But putting 6 of them together, same engine, gives this airplane its tremendous speed. You can see modern examples of something like this. For example, today's B-1B has 4 of the same approximate types of engines that the single-engine F-16 fighter has. So think of a B-1 in terms of power as about 4 F-16s. Same with this thing, it's got 6 fighters worth of power. This is the guts of the XB70's power. This is General Electric's YJ93 afterburning turbojet. This engine weighs a little more than 2 tons and develops a maximum of about 30,000 pounds thrust. It's got an 11-stage air-cooled compressor and a 2-stage turbine. One of the unique things about this engine, unique for the time anyway, is that the afterburner, though it looks like any afterburner, is not controlled through cable linkages. This afterburner is controlled electronically because you've got 6 of them to control. That's a big task for any pilot. And so think of 6 of these 2-ton engines together, each developing 30,000 pounds of thrust, and you get a really, really fast, big airplane like the XB70. An interesting part of the trailing edge of the XB70's wings is the series of elevons, combination ailerons and elevator along the trailing edge of both wings. These are for latitudinal and longitudinal stability. And it was designed with these trailing edge elevons to be split into 6 segments on either side of the engine bay. And they're operated by no fewer than 24 separate hydraulic jacks. By the way, the elevons are operated only hydraulically. There's no manual reversion for the pilot if the hydraulics fail. But again, they operate as elevator and aileron both. You can see the XB-70 and hundreds of other interesting, exotic, and historic aircraft here at the National Museum of the U.S. Air Force. And if you can't get here immediately, you can go on our website and see all the same stuff. And you can even get inside the cockpits with our Cockpit 360 application, where you can look around the inside of these airplanes, including the XB-70. So I encourage you to visit and to visit our website. It was a complex airplane. Like other airplanes of its era, it was full of analog dials and gauges. And so every pilot knows that there's a kind of a habit, a system of scanning the instruments to make sure that everything's okay. Well, think of that job inside the XB-70. 6 engines. A flight regime anywhere from 150 knots to Mach 3, with high-speed cruise at Mach 2 or Mach 3 preferable for the airframe and the engines. Plus, you've got a control system that is dependent on these forward canards, elevons in the back, folding wingtips, and so on. So this is not your average airplane to fly. It was perhaps a little tricky and unusual. However, the 7 people who flew that aircraft were well acquainted with unusual flying situations in unusual vehicles. So it wasn't a big surprise for them, but it would probably overwhelm the rest of us. The crew accommodations in the XB-70 might not be what you'd expect. You might think, wow, in such a fast, high-altitude airplane, they're going to be wearing spacesuits. Well, not so. The XB-70's crew cabin was air-conditioned in a shirt-sleeves environment. The temperature in there at any speed was something between 70 and 100 degrees Fahrenheit, so it was a shirt-sleeves environment. However, if they experienced decompression at high altitude, each of the crew members, the pilot and co-pilot, they each had a separate kind of clamshell enclosure, very similar to the one in the B-58, that would automatically close, and then from inside of that pressurized enclosure, the pilots could monitor the instruments through windows in this little clamshell, and they could bring the aircraft back down to a safe altitude. They had controls inside the little clamshell. Once they were at a safe altitude, they could open the clamshell back again. Now, if they had to eject from the airplane, the whole clamshell, both of them, would come out of the airplane, out of the top, like an ejection seat. The U.S. government encouraged supersonic airliner progress with its National Supersonic Transport, or SST, program. NASA used the XB-70A as its primary aircraft in this SST investigation. In 1971, though, the American SST program was canceled. Why? Well, that was in part due to the problem of sonic booms on the ground. Sonic booms are loud, explosive noises caused by aircraft flying faster than the speed of sound. However, later in the 1970s, the supersonic British and French Concorde aircraft entered commercial service, And even the Soviet Union briefly operated the supersonic Tu-144. So the lesson of the XB-70 and SST research is that those ideas in aerodynamics and materials and high-speed control were carried from military aircraft ideas to civilian airliner design and operation.